In this lecture, we're going to talk about the singular value decomposition. So we've already looked at eigenvalues, and you might remember from linear algebra. Of course, we've talked about how to compute them numerically in this class, but from linear algebra, you might remember the eigenvalue decomposition that says we can take a matrix A and we can decompose that into Q lambda Q transpose. So these are all matrices. The Q's are matrices of the eigenvectors, and the lambda matrix is just a diagonal matrix with the eigenvalues on the diagonal, and zeros in the off diagonal. And we've learned if A is a positive symmetric definite matrix, then we can use the tools that we've discussed so far to compute this decomposition. But more generally, if we don't have a positive symmetric definite matrix A, or if A were a rectangular matrix, meaning that there's more columns than rows, for example, then the eigenvalue decomposition doesn't really have a meaning. So the singular value decomposition is just a generalization of the eigenvalue. It's a decomposition of the matrix A into an orthonormal matrix U, a diagonal matrix sigma, and an orthonormal matrix V, where sigma is once again a diagonal matrix, this time containing the singular values and the singular values are the eigenvalues. So I'm going to say the singular values, the sigmas, are the eigenvalues of the matrix A, T, A. So even if the original matrix A were not positive symmetric definite, or if it were a rectangular matrix, if you perform the computation A transpose A, then what you're going to end up with is a square positive symmetric definite matrix. Therefore, if you go ahead and use the tools that we have to compute now the eigenvalues of this symmetric positive definite matrix, what results are the singular values, okay? In the event that the original matrix A was a square matrix of full rank, then the relationship between the singular values, it's just that they are the square root of the eigenvalues. So that gives us a way, even if A were originally a rectangular, a square matrix, we could then go ahead and compute the eigenvalues using the SVD. In the event that, say, A were rectangular or something like that, then the remaining entries would be 0 here. Okay. U are the eigenvectors of A transpose, and V are the eigenvectors of A transpose A. So then once we have that, we can use this type of thing to decompose A into, again, an orthonormal matrix that are the eigenvectors of A transpose, a matrix epsilon, which is diagonal. The diagonal entries are they're the eigenvalues of A transpose A. Turns out they're also the eigenvalues of A transpose. They have the same eigenvalues. If A was a square matrix of full rank, then the relationship between the singular values is that they were the square root of the eigenvalues of A, right? So if you compute the singular values, then you can just take simply square them, and then you'll get the eigenvalues of the matrix, of the original matrix. Okay, and then of course V is the eigenvectors of A transpose A. So, and it's also orthonormal. So what is this used for? It's used a lot in image processing. It's used to compute an effective rank. This will be the case if you had a square matrix. Polar decomposition, least squares problem. So, the best fit to data, it can be shown that this is really closely related to that. Pseudo inverse, that would be the inverse of a rectangular matrix. And my favorite, the algorithm that computes eHarmony's 29 dimensions of compatibility. And there's actually a patent associated with this, which is really funny because they essentially patent a mathematical algorithm. The 29 dimensions of compatibility, what they do is ask you to fill out a questionnaire. The answers from those questionnaire are then put into a matrix form, and the singular values of that matrix are computed and then compared with another person's. And the closest match to the singular values, essentially, that's how they choose the people that they believe to be closely related to. So they actually patented a mathematical algorithm, which is interesting. Again, we already have all the tools we need to do the SVD, and that is we use the QR method to find the eigenvalues of A transpose A. Once we have those eigenvalues, those are the singular values, we can use the inverse power method to find the eigenvectors of the matrix A transpose A. That will form the matrix U, and then do it again for the matrix A transpose. I think I said that backwards. So if we do it for A transpose A, that form the matrix V, and if we do it for A transpose, that form the matrix U. And then once we have those, we can use the Gram-Schmidt method to orthonormalize those vectors U and V. So then we'll have the complete SVD. So we already know there's no new algorithms here. It's just basically combining those algorithms to get the SVD. On the very first lecture, when we started talking about numerical methods, we mentioned a matrix's condition number as its sort of amenability to numerical computation. So what a condition number is the ratio of the maximum to the minimum singular values. And if it's a very small number, then that system would be more prone to instabilities. And so what that means in solving a system of equations, say ax equal to b, is that the relative error of x is going to be the condition number times the machine epsilon. The relative error is going to be smaller than the condition number times the machine epsilon. And so this, of course, if the condition number is 1, then you can actually essentially drive the relative error to machine epsilon if desired. And so in the event that we have poor condition number, we can use something called a preconditioner. And so this is, instead of solving the original system, ax equal to b, of course we can multiply both sides of that system by a matrix P inverse without changing it. And we do this to try to improve the condition number of the system. The best, of course, we have to compute an inverse here. And so, the easiest thing to compute an inverse would be simply the identity matrix, right? So if we just had that P is equal to I, well then P inverse is also equal to I. But then if we multiply this system of equations by I, we don't do anything, right? So this is the simplest to compute, but it doesn't change the system at all. The most difficult to compute would be to choose P equal to A, and of course then P inverse is equal to A inverse, which is the same thing as just directly solving the system of equations, right? Using a direct solver. And there's no point in really doing that either. So typically what our preconditioner is something sort of in the middle, right? It's something that balances the ease of inversion with the improvement in condition number that you would get if you actually inverted A. And so if we typically use these preconditioners with iterative solvers, and again, for sparse systems with a preconditioner, we can usually, iterative solvers can usually outperform a direct solution technique in terms of speed. So just a final thought here. If you go and you write really highly optimized code in C, C++, or Fortran that do linear algebra, you're going to use a compiled library likely called LAPACK or a various implementation of it. And so there's functions built into LAPACK that can perform all of the types of computations that we've performed in this class. And so here, this is just a few of the ones that we've covered with their LAPACK function calls, and you can look at the documentation on those for more details and the corresponding, Python, NumPy, SciPy implementation. And many times, in fact, the NumPy, SciPy implementations are just wrappers around the actual compiled C or Fortran LAPACK calls to do these kind of various operations. So I just wanted to finish our discussion of numerical linear algebra with this kind of thing, and you can use these as a reference to get started and go on and look at many of the other implementations of matrix operations, linear algebra operations in LAPACK and NumPy, SciPy.